I'll be describing joint work with Julia Rubin. Both of us are from IBM Research on a Bayesian approach to privacy enforcement in smartphones. And I'll start with some motivation. We all know that mobile apps have a lot of access to our sensitive information. It could be contextual information like our location. It could be device identifiers, users identifiers, social information like our Facebook accounts, our contacts list, and so on and so forth. And just by looking at an application, it's really hard to say what exactly it does. In this particular example, it's an application that was designed to steal users' credit cards. It's really hard to tell from the outside what exactly the application is doing. But maybe even if you have a better idea what the application is doing, maybe if it's Angry Birds and it still wants access to your private information, be it for analytics, for advertising, for different use cases, then there's maybe another interested party, in this example, the NSA, who may want to build a persistent profile of the user, get a better understanding of what the user does, and all of this is based on information that perhaps you don't feel so comfortable sharing with other people. So here's an example of a benign app doing things that sort of make sense and still feels problematic. And indeed, in some recent statistics published by Veracode, their annual security report, we see the information leakage in the mobile environment is a big deal. We see that in Android being one of the top 3 security threats in the Android platform. In iOS, we sort of move up to the very top of the list, with 62% of iOS apps having different kinds of information leaking behaviors. And also in Java ME, we have these kind of alarming statistics, and which actually sort of persist across different platforms, not just mobile, but web and others with information leakage. And what's even more disturbing is that even if we look back at recent years, we see that not only is it there now, but it's been there also before and sort of with similar numbers, which means that there's not much change, shift, or improvement in securing user privacy on mobile platforms. And so this is the motivation we're coming out of. And I want to sort of take us deeper to the technical level with an example, a real-world example coming from an Android library with slight revisions just for the purpose of this talk. So this piece of code reads the user's address. It then reads the user's SIM ID. It runs some checks on the SIM ID, and if it's bad, then it may log certain information to an error log. And otherwise, or just in any case, it logs other pieces of information to the standard log file. And looking at this example, sort of analyzing the information flow behavior in this example, we can make 2 observations. The first is, in both cases, there's information flow coming from a piece of sensitive information, the IMSI, the user's address, and going into an observation point or sink that releases information to the outside. But there's also a difference between these 2 examples. In the first case, or these 2 flows, in the first case, we see that information pretty much flows as is to the release point, identifying the user uniquely. In the second case, there's more work being put into anonymizing information that goes outside. It would be the X's padding the end of the suffix of the IMSI. It would be the fact that there's only the country that's released and not the entire address of the user. And so we sort of want to distinguish these 2 cases, and we sort of want overall to create an enforcement solution that is able to disambiguate cases where really the application took the necessary steps to protect user privacy or just release a sufficiently minimal amount of information versus cases where really information flows outside and maybe really compromises the user. So sort of disambiguate these 2 cases and give the user the sense of privacy they want, but in a kind of usable way that doesn't flood the user with false alarms. It's kind of the motivation we're coming out of. What I want to sort of qualify here is the scope of this work. We're assuming benign applications. And what I mean by benign applications is maybe the application releases the information for advertising, analytics, social computing, cross-application profiling, and other use cases of this sort. It's not a malicious application. It's not trying to steal your information. And what this means is if the application is releasing the information outside, then that would be in some kind of a standard form, maybe plain text, maybe some kind of standard transformation or encoding, but there's no sophisticated attempt to leak the information out in a way that's completely disguised. Still, doing all these things often happens in an unauthorized kind of way without the users knowing what actually are the pieces of information aggregated and flowing out, combined, and if it's done in a way that is perhaps too direct, too explicit, and too unique to that user. So that's the scope for this talk. And the perspective we chose to take in this work to sort of distinguish different behaviors that have to do with information flow is a Bayesian perspective. Just to sort of motivate the intuition, we sort of want to treat information flows into sinks, or the fact that potentially sensitive information reaches a sink, as kind of a conditionally legitimate or a conditionally illegitimate event. It may or may not be wrong depending on evidence that we have available at the point where the information is released. And this is sort of our starting point for this research. And to make it more concrete with the logging example we saw before, we know which statement or which string is about to be released, written into the log, and we basically want to look at it as two possible probabilities or measures of what's going on. It's either legitimate or illegitimate given some pieces of information. If we want to encode taint analysis into this setting, then all we have to say is our evidence available at the sync point is the taint tag, or the tag that sort of denotes that it came from a privacy source and reached that point. And so this gives us a very kind of simple and qualitative determination what's going on. If the string is tainted, then there's a problem, and otherwise there isn't. And it sort of feels too conservative because we see that in this case, effort has been taken to protect the user, and it's not just enough to check if the string reaching the sink is influenced by user input. We sort of want to account also for, in some notion that I'll try to clarify throughout this presentation, we sort of want to quantify the amount of information being released outside. Some notion of distance that sort of captures the fact that really there is flow of information to the release point, but really it has to do only with the country and only with a prefix of the user's SIM ID. Now, of course, we can also encode taint information into our judgment, but the point is that we take also other pieces of information into account when making the determination. And another thing we have to clarify when stepping into this kind of Bayesian classification setting is exactly how we quantify all this probabilistic expression. How do we derive all these pieces of the Bayesian classifier to actually reach a decision at the sync point and do that, of course, efficiently? So I'll start with a series of WH questions that sort of try to clarify what we've done in this project. And the first being why. I think for precision, we already gave the motivation. There's different forms of release of information that may or may not be, they may release different amounts of information. But another thing we're hoping to achieve, and I hope I'll convince you that we managed to achieve, is robustness, in that in some cases we're able to remove the need entirely for taint tracking and really look at these value-based similarity features to decide if and what has gone wrong without the need for intrusive taint instrumentation over the entire program. Moving on to how we sort of want to compute these distance metrics between values read at privacy sources and values reaching sync points, but we also want to do that in a way that bounds the cost of the analysis and makes the results we obtain through this kind of analysis persistent across computing a classifier and using a classifier in practice. And what this means is we want to sort of bound the judgments we do in more than one dimension. We want to bound the distance metric by the arguments reaching it. We want to bound the privacy features by some constant. And we want to bound the comparisons done with respect to the private values. And that altogether, what this gives us is some kind of a bounded notion of the comparisons we have to make when computing a classifier and when using a classifier in practice. And in particular, two string metrics, very well known, very simple ones that we experimented with for the purpose of this study are Hamming distance, which is a really simple form of comparison between two strings to quantify distance between them that simply looks at substitutions, and a slightly more sophisticated comparison metric, which is Levenshtein distance, which also enables insertion and deletion of characters within the strings to sort of understand how much of an overlap there is between them. The third WH question that I want to answer is when do we compute all these different pieces that actually fall into the leakage judgment? So we have this conditional expression, and the first piece that's sort of like the nicest for us is what we're not going to do. And what we're not going to do is we're never going to compute the denominator in this expression, simply because we're computing two conditional expressions that have the same denominator in order to decide whether the leakage event is legitimate or not. So far, our life is easy. Moving on, we have to compute another piece of the classifier, and that, of course, we want to do offline. And the reason is we don't want to expend any effort online, and we sort of want to have a stable classifier to be equipped with the stable classifier that we've computed already when coming to make real-time judgments about privacy. And here, basically, the question we're asking for this component in the expression is how likely is a given API to participate in legitimate versus illegitimate behaviors. Here, we're just falling back on existing literature and published statistics. We haven't done any analysis of our own to quantify this part of the expression. The third part of the expression for which we had to work the hardest is to say for different valuations of these features, of this overlap between privacy values and values arising at sinks, how likely are they to be there based on the legitimacy of information release? And here there was no escape. We had to actually sit down, take 35 different applications that we sampled at random and compute these empirical probabilities as we describe in more detail in the paper. So overall, we have this classifier that we compute offline, as I explained, for the different pieces. And we have this motivation for trying to take a more fuzzy approach to privacy judgments. And what this gives rise to overall is the following algorithm. When a source statement is invoked, and again, sources and sinks, as I described them here, are up to a specification. The algorithm is, of course, parametric in that specification, similarly to other works. When a source statement is invoked, we derive the privacy feature, namely the value of the private item obtained by the source. And we then start tracking that value through a taint tag. This goes on with the standard data flow equations for propagating taint information across the code. And then when we reach a sync point, we utilize these tags to understand what we need to compare to the value read at the source statement in the sync. And this we do to derive our different valuations for the features. And as I said, we're going to bound these valuations to be able to actually utilize classification information computed offline. And finally, what we do is we simply compare two measures according to our classifier computed offline to decide if we want to trigger an alarm or not. But this sort of glosses over some details that I sort of committed to at the beginning. The first being that we said that we can go beyond plain text. So all these string distance comparisons work very nicely with plain text, but we sort of, without dealing with malicious applications, we're still intending to support standard transformations. And the solution to this is easy, actually. All we have to do, because these are standard transformations, instead of just obtaining the reference value for a feature, the value actually read at the source, we can also encode it in different forms and perform the comparisons over the encoded values. So that one's easy. Another challenge is we sort of assumed, to simplify the setting, that we have feature values that are bounded. But in reality, it's not necessarily the case. So what we're going to do to simplify, to obviate this problem, is we're sort of going to say, we're going to compare the distance between values up to a bound. And from that bound on, we're just going to say, we're just going to introduce a constant that says they're too far apart, and that's it. And this already lifts that problem. And the third, and perhaps most exciting to us, feature that we built on top of the core algorithm is to remove taint tracking, to actually be able to perform privacy judgments without intrusive taint tracking. And although taint tracking is very useful, and although it's shown very promising results so far, there's also the fact that that it takes a lot of subtle engineering to tune down the overhead, and that there's also stability issues when you instrument an application. And so to us, this was a big goal of us, to be able to sort of fall back on value-based comparisons and sort of tone down the taint tracking part of this. And what we're doing is a somewhat simplistic solution of just saying we don't have the taint tags to propagate around. We don't know what to compare, so we're just going to compare the value read at the privacy source to sync arguments and values reachable from sync arguments in a somewhat naive way up to a bound. And this turns out to work really nicely in practice. So with all these pieces together, we set out to test out two experimental hypotheses. The first being that with our approach, we can gain better precision and overall comparable results in terms of coverage and false negatives to taint analysis. And for this part of the study, we took Droid Bench, which is, to what we know, the most mature privacy benchmark suite available by Eric Bott and his team in Germany. We excluded certain benchmarks that either had bad behaviors because they were designed for static analysis originally, or we could not reach callbacks with privacy that actually leaked the information. And we compared with TaintDroid. And the results we obtained are in large part encouraging. We had many less false positives compared to TaintDroid on the one hand, which made our precision score much higher. On the other hand, we had two false negatives that TaintDroid didn't have, being, in a sense, more low-level in tracking taint bits rather than the value-based comparisons. But what's somewhat encouraging to us is that these false negatives actually come from custom transformations over data, which to an extent is out of scope for us. We're designed to support standard transformations rather than more sophisticated attempts to leak data unnoticed. So that's one piece of the evaluation. The other piece of the evaluation is to actually take this exciting news that we're trying to bring out, which is maybe we can do leakage analysis while relaxing taint tracking and do it based more purely on value-based comparisons. And to experiment with this, we took out of the 100 topmost Google Play apps that we originally started from, 35 went into our training for the classifier, 65 remained, out of which we filtered out some apps that were either uninteresting or not stable enough for our dynamic experiments. And we compared two versions of our system, one which we call TBD, which is based on taint tracking, as I showed for the core algorithm, and another one, HBD, which is based on this heuristic notion of just trying to compare between values arising at the source in the sink heuristically up to a bound. And what we saw here is, interestingly, we saw that we have many more cases for at least certain types of privacy features where we're able to detect the problems, but not the taint-based approach. The reason being fundamentally not because the taint-based approach has more likelihood to have false negatives. That's not the reason. The reason is purely stability. Our system was more stable and able to reach judgments over more parts of the code that with instrumentation were sometimes missed, and we have a discussion of this in the paper. I would note, though, that there's one false positive by our approach that was not, by the HBD variant, that was not reported by the TBD variant. So in conclusion, what we try to do with this project is to generalize beyond taint analysis to a Bayesian classification framework that allows us to encode taint analysis, but also allows us to factor other dimensions into privacy judgments. The main other dimension that we were concerned with is value-based comparisons, and taking it to the next level, what we tried to build is design a system that's based purely on value-based reasoning and can obviate to a large degree any need for information flow tracking in real time. And we have plans, and IBM is sort of prohibiting me from saying anything more, but we do have plans to integrate this into an IBM security product we're offering in the future, so that's going to be cool for us. And thank you very much. I'll be happy to take your questions.
So with such a small sample size, what kind of efforts do you make to not overfit? Do you have some sort of intuition of like a regularization of these sort of parameters that you're tweaking, like maybe the depth or maybe you could do a grid search for a better prior? Like what's the trade-off here and how do you actually assess? Because do you fear that you're overfitting with such a small sample size?
So I think that's a good question. We did have the fear that because it took a lot of manual work, we had to restrict ourselves to a fairly small benchmark suite and a fairly small amount of applications that we used to train the classifier. The good news, though, is since we released this capability as a prototype, we had much more extensive experience with it. since it's going to go into an IBM product, and we didn't see any overfitting trends moving to a much larger scale of data. So you're right, the threat was there, but it's not confirmed in practice, so that's good news.
I guess one quick question, which is, I know this is going into a product, but one reason, one of the many reasons that, like, for example, TaintDroid has had a lot of research impact is that people have been able to do follow-on research very easy because it's released. Are you guys also going to make your stuff available to the community?
I'll tell Julia you said it's easy.
What?
I'll tell Julia you said it's easy. No, just kidding. It's great that it's out there, and it's great that it's documented. Yeah. No, I was just making this comment because it took some struggle to deploy it. But yeah, I'm giving 100% to Will Inc. and the other contributors that the product is out there and it's available. And what we hope we've done is we've created a simple enough solution to be recreated outside our own implementation by others so that it's available for experimentation. The details are in the paper, and it's a fairly easy system to implement. So I hope at least that's, that goes to some extent toward what you were hoping would be.
All right. Thank you very much, and thank you guys for staying till the bitter end, and see you at the reception.